In this lecture, we will discuss some important graphs and will also see graphical representation of charge carrier concentration. In the leftmost graph, we are having the graph of density of states per unit energy per unit volume, represented by G, which is a function of energy. In the conduction band, it is Gc, and in the valence band, it is Gv. In the middle, we have Fermi-Dirac priority function graph. First, we are going to discuss for intrinsic semiconductor, and you have studied in the previous lecture that in intrinsic semiconductor, Fermi energy level is equal to E mid value plus kT by 2 into natural logarithm of Nv divided by Nc, where Nv and Nc are the effective density of states in valence band and conduction band respectively. So, for intrinsic semiconductor, Fermi energy level is not exactly at the middle. When the temperature is 0, then only the intrinsic Fermi energy level is exactly in the middle of EC and EV. Now, we will assume that the temperature is raised to such value so that the Fermi-Dirac priority function graph comes out like this. And also we know that the electron concentration is the integral of Gc multiplied by Fermi-Dirac priority function value at energy E. Graphically, we can say we have to multiply the first two graphs to give the product Gc into Fermi-Dirac priority function, and to find the electron concentration, we have to find the area of the resultant curve. Also, you can see that the density of states which are useful is only up to this point, as after that the Fermi-Dirac priority will be 0 and the product will always give 0 value. Now, if you want to plot multiplication in the conduction band, then the plot will roughly look like this. In valence band, we have to multiply Gv into 1 minus Fermi-Dirac priority function. This particular function gives us the priority of an energy level being occupied by a hole, and integrating it will give concentration of holes in the valence band. Here also, we are supposed to multiply the first two functions Gv and 1 minus f, which will give hole concentration to be like this. And since we have taken intrinsic semiconductor, the area of this curve will be equal to the area of this curve, as the area of the upper curve represents free electron concentration, whereas area under the lower curve represents the hole concentration. And also, for intrinsic semiconductor, both concentration are equal. Now, can you tell if there is any point which represents effective density of states Nc and Nv? Actually, there is no such point, as effective density of states Nc is assumed to be present entirely at EC. Similarly, effective density of states Nv is assumed to be present entirely at EV. So, even if we want to represent Nc and Nv, then it needs to be placed exactly at EC and EV. Observing carefully, you can see that even though Fermi priority between conduction band and valence band is having a finite value, but still there are no stable quantum states. This is because, as studied previously, there can be electrons present between conduction band and valence band, but they are highly localized and they stay there for very small time, and we are interested in only those electrons which increases conductivity of the crystals, and hence there are no allowed quantum states between conduction band and valence band. We will do the similar analysis for N-type and P-type semiconductor. Even though the diagram is not complete, you can still tell that this diagram is of N-type, as the Fermi energy level is closer to conduction band energy level. Similarly, the lower diagrams are meant for P-type semiconductor. Now, we draw the rough plot for Fermi-Dirac priority function in P-type and N-type semiconductor. You can observe the area in the conduction band for the Fermi-Dirac priority function in n-type semiconductor is more. Product of Gc into Fermi Dirac function in the conduction band of n-type semiconductor will look like this. And you can see that 1 minus Fe in the n-type semiconductor have very less value below the valence band. So the multiplication value will look like this. This represents the electron concentration and this represents the hole concentration. Obviously, for n-type semiconductor, free electron concentration is greater than hole concentration, and the same can be easily observed in the graph also. Doing the same analysis, we can find the graph for electron concentration in p-type semiconductor to be like this, and hole concentration will come out like this. This area represents free electron concentration and this area represents hole concentration. For p-type semiconductor, P0 is greater than N0, which can be easily observed in the graph also. That's all for now. I hope each and every graph is clear to you and you can solve questions relating to these graphs.